Hello, my name's Daniel, and this is my Lab 6 report. For this lab, we investigated how a magnet interacts with a conducting tube through the phenomena of electromagnetic induction and Lenz's law. When a magnetic dipole moves through a conducting material, the changing magnetic flux induces currents that oppose the motion of the magnet. This produces a magnetic drag force that slows its fall. The primary physics principles used in this experiment were Faraday's law of induction, Lenz's law, and a magnetic field of dipole, which we previously studied using the Biot-Savart law. The goal of the experiment was to compare the actual fall time of the magnet through an aluminum foil tube to a computational model created in GlowScript. By adjusting parameters such as tube geometry and dipole moment, we matched the model to the measured behavior and analyzed sources of discrepancies. Here are the results. So the system of the experiment was the bar magnet and the aluminum tube, and the surroundings were everything else. The materials used were an aluminum tube, a bar magnet, 1 yardstick, and a timer. So first, to conduct the experiment, we first measured the dimensions of the tube. This includes the tube's total length, the width of the foil strip, and the radius of the tube. And these values were later added into the computational model. We then dropped the bar magnet 3 separate times from the top to the bottom and took the average of each time recorded. In our experiment, the fall time was approximately 1 to 2 seconds, significantly slower than regular free fall. We then made a computational model using GlowScript, where the bar magnet was used as a point dipole. The aluminum tube was used as a stack of conducting rings. The induced current in each ring was calculated via Faraday's law, and the simulation calculated velocity, position, induced currents, and net magnetic force over time. Here we can see that we adjusted the parameters of the length of the tube and the width of the tube. We also had to adjust the dipole moment for the bar magnet in order to get the simulation to match as closely as possible to the actual experiment. So with the experiments conducted, they showed us that the magnet fell much more slowly than the conducting tube than it would in free fall. This is consistent with the electromagnetic braking predicted by Lenz's law, which is that induced currents produce magnetic fields that oppose changes in magnetic flux, resisting the magnet's motion. In the initial version of our computational model, the fall time was only about 0.38 seconds, which is far too fast and more closely resembles what an object falling through a tube would be in free fall. So after correcting the dipole moment and using a realistic foil thickness, the simulated fall time increased to about 1 to 2 seconds, which we can kind of see here in the corner. The simulation also showed decreasing velocity over time until reaching a terminal speed, confirming that the magnet experiences magnetic drag proportional to velocity. There are some possible sources of error. It's possible that aluminum foil thickness was different from what we assumed it was. The computational model approximated the tube as discrete rings rather than a continuous conductor. External magnetic fields were not included, including the Earth's magnetic field. So there may have been a small misalignment that may have caused off-axis motion of the magnet, and possible imperfect electrical contact between foil layers could have increased the resistance. So what if the resistivity of the conductor were reduced as close as possible to zero, and how would the dynamics of the falling magnet change? So if the tube's resistivity approached zero, the induced currents would become extremely large. These currents would create very strong magnetic fields opposing the magnet's motion, greatly increasing the magnetic braking force. The magnet would fall much more slowly, and in the ideal limit, it might barely enter the tube or appear to hover because any change in magnetic flux would be almost perfectly opposed. Finally, what if holes or slots were cut into the tube, and how would this affect the ring currents in our model? So cutting holes or slots breaks the closed conducting loops needed for currents. With interrupted paths, the induced currents become much weaker or disappear entirely. This reduces the magnetic braking force so that the magnet would fall faster, closer to free fall, compared to a continuous tube. That is it. Thank you for watching.